ado, I will pass it over to Professor Gianani.
Thank you, Ephraim, for the introduction and for the invitation as well. I'm very happy to be here today, and thank you all for joining. So yeah, as Ephraim said, today I'm going to discuss some results we got on thermodynamical simulation and the energetic cost of quantum logic gates. The results I will present are all based loosely on the Landauer's principles, so I will start by introducing that. And then I will give you some background on why we need to do simulations on these matters, why we choose quantum optics as a platform for the simulations. I will briefly introduce some concepts of quantum metrology and then go into the results to show you that informational and thermodynamical quantities are strictly linked, and this link works both ways. So we can infer from informational quantities thermodynamical processes and the other way around. Okay, so as I was saying, it's all based on Landauer's idea, which is that information is physical. And this is captured by Landauer's principle, which states that if you want to erase a bit of information, there's an energy required for you to do so, a minimum energy required for you to do so, which is what you see here. Do you see my pointer? Yes. If I move the pointer, do you see it? Yeah, cheers. Okay. Based on this criterion, a solution for what is one of the long-standing paradoxes of thermodynamics was proposed, which is the Maxwell's demon paradox, which briefly states that if you have two chambers filled with particles at slow and fast particles, so two different temperatures, if there is a demon who can act on the aperture between these two chambers, and by gathering information on those particles, move all the fast particles on one side and all the slow particles on the other, you would create a temperature gradient and end up in a situation where you have decreased the entropy of your system, which would contradict the second law of thermodynamics. A possible solution to this paradox is considering as your system not only those chambers, but also the memory of the demon, which in the meantime has gathered the information on the particles. So if you want to go back to the initial state, you'd have to erase the memory of your demon, and in doing so, you would increase all the entropy that you decreased by only considering the chamber system. So as I was saying before, the results I will present today are based on this concept that information and thermodynamics share a lot of similarities and are very well interconnected. And in particular, this works both ways. So we will use informational properties to simulate and to discuss thermodynamical processes. But we can also, once we have our informational platforms, our logic gates, use thermodynamics to increase our knowledge on those platforms. I will show you some results we have in the recent years, but if you want to have a more in-depth view on this topic and you are interested, a good reference is this book, which I've put here, and I can give you the details if you want. So the framework in which we will work in is that of quantum thermodynamics. So we have our system, which is initialized in a state of 0 and evolves in time. And during this evolution, it can exchange it and work with the environment. So its Hamiltonian is changing, and you can write change in time in the Hamiltonian done by 2 bits. So one where is the system that is changing and one where is the Hamiltonian that is changing. The first corresponds to a change in the heat of the system, and the second on work performed on the system. So you can easily retrieve the first principle of thermodynamics just by saying that your system is evolving. So this is, however, if we are interested in seeing one particular process of exchange of heat or work, whatever, and we want to isolate that particular process, this can be really hard, because if our system is interacting with the environment, it can be interacting in many ways. And so we want to be able to isolate that particular contribution. So we need to simplify our problem and find our spherical cow approximation of the problem. And the requirements we need are the following. We need a simple quantum system and a controllable one. So the simplest system we can think if we are thinking about energy exchanges is a two-level system. And that is fine. We have many examples of those. But as I was saying, we need a system where we can control the dynamics so that we don't have any unwanted interactions. And a solution to this is simulating the dynamics in a way that we can actually control that only what we want is happening. So the problem transposed to finding a way to map our two-level system into another degree of freedom of which we can control the dynamics. One possible solution for this degree of freedom is to choose something related to photons. This is because it's really hard to make photons interact, so we really struggle to do that. So when we do, we are sure that there's not going to be any other interaction we don't want happening at the same time. In order to do so, though, we need to generate our single photons. So we have to have our single quantum objects to then control. This is done through, for example, through spontaneous parametric down conversion, which works in this way. You have your laser beam coming in a nonlinear crystal. Most of the time, nothing happens, and the laser just goes through. Every once in a while, a photon from the laser is split into two photons with in frequencies, and so you produce your single photons in this way. If for those of you who have not worked in a quantum optics lab, this is how SPDC source looks like. You have your laser coming in from the left, and this is your nonlinear crystal. After your nonlinear crystal, you still have a lot of your laser going through, but you also have your photons, which you cannot see, which are collected by these two mirrors here. And then you send it to other mirrors, and then you do with them whatever it is the experiment you want to do. So this spontaneous parametric down conversion process has to respect two important conservation laws, which are the energy conservation first. So you are coming in with a laser at a certain frequency, and the frequency of the upcoming of the outgoing photons which you generate have to sum up to the energy of the photon that has been converted. So the way that the energy is shared between these two photons is non-trivial. So it can be, you can have degenerate photons in energy, but you can also have other modes, basically. So your photons will be anti-correlated in frequency as a result of that. The other conservation that needs to be, that applies is the momentum conservation. So you will basically have, you will know at what angle your frequency, your photons will be generated. Another important feature is that since for the nature of the process, you always generate photon pairs. So if you have one photon, you're sure there is another one, basically. Okay, so once you have your photons, you can control and encode the information you want in different degrees of freedom. For example, you can use your spatial profile, and in this case, you can choose as a basis, for example, orbital angular momentum modes, or you can encode your information in the time frequency domain. And if you do so, you already know that, as I told you, your photons are anti-correlated in frequency, so you basically get entanglement in time frequency for free while you generate your photons. But the most used one is for sure polarization, because it's the easiest to control, even from a technological standpoint. And in particular is the one we are interested because it lives on a two-dimensional Hilbert space. So it's a two-level degrees of freedom that you have. And you can so then map your ground and excited state of your thermodynamical system into two polarization states of your photons. For example, vertical and horizontal in this way. By using quantum optics to simulate your problem, you sure have a simple and controllable quantum system, and you have no unwanted interactions because photons are non-interacting particles. And this is what the requirements we actually were looking forward to. But there is an added bonus, that is that quantum optics is a good platform for quantum sensing. And so you have all the knowledge coming from quantum metrology, which can be used for our purposes as well. So we'll just give you some brief details on how on meteorological quantities that we will later use. And to do so, I will introduce parameter estimation. So basically, all experiments result in having to estimate a parameter. The way we do that is that we record the probability distribution of our measurement outcomes K, conditioned on having our parameter lambda to begin with. So this is how the probability distribution can look like. If the probability distribution is narrow and centered around the true value of lambda, then we have done a good experiment and our error will be small. If this is spread like the red one you see here, we will have a bigger error. This concept is captured by the Fisher information, the classical Fisher information, which it depends on the probability distribution I've just described in this way. And from the Fisher information, we can infer a lower bound on our error, which is the Cramer-Rao bound, and goes like 1 over m times the Fisher information, where m is the number of resources you are using for your measurement. Okay, so the scheme for doing parameter estimation is very simple. It's a 3-step scheme. You have to prepare your probe in a given state. You have to make your probe interact with the system, and then you have to measure your probe to extract the information. The Fisher information, the classical Fisher information, which we have just seen, is strictly related on this last process because, as I told you, it depends on the measurement outcomes K, so it will surely depend on what measurement we perform. However, when we're dealing with a quantum system, we can also introduce the quantum Fisher information, which will only depend on the state we are using as probes. We can calculate it, but the important thing is that the quantum Fisher information is optimized over all the measurements we can perform, so it's independent of the measurement. And so it will be for sure greater than the classical Fisher information. In this way, we can identify a quantum Cramer-Rao bound, which will lower bound, which is our ultimate bound of precision, which will analogously to the classical one be given by 1 over m times the quantum Fisher information, and m is simply the number of resources we are using again for our measurement. Okay, so how do we go from this? Sorry, yeah. I don't hear you, Ephraim. Sorry, you are muted.
I'm sorry.
Okay.
The question is what exactly you meant by resources?
Is the number of probes that interact with your sample, basically. That is a way for defining it. That is a lot of there are different ways, but this is one we can use. So once you have your information protocol, how can you use this for thermodynamical purposes? If you can recognize from this protocol that this is the same thing that you do when you do a thermometer scheme. And you can use whatever probe you like. You can, in this case, well, you can use a cat as a probe. The important thing is that you follow your protocol. So you have to prepare your cat in a state. A live cat is one which sounds appropriate. You need to make your cat interact with the system. And you can then measure a property of your cat, in this case, the length of your cat, which will be a function of the temperature. In our case, we won't use a cat as a probe, but we will use a single two-level system, so a qubit probe, and we make it interact with a thermal bath. The first thing that we can do before estimating the temperature is discriminating between two temperatures. So we make the probe interact with the bath, and then we want to measure the probe and find out if the bath was cold or hot. How do we model the interaction between the probe within the probe and the thermal bath? We can use the generalized dumping channel, because when the probe interacts with the bath, only two things can happen. Either it decays from the excited state to the ground one so this is modeled by the amplitude damping channel, which happens with a probability P, and is and the decay rate, which is called gamma, or there's the inverse amplitude damping. So the probe goes from the ground state to the excited one with a probability 1 minus P, and a decay rate, always gamma. So we have this, if we mix these two processes, we can model our interaction with the thermal bath. And these are the Krauss operator which describe them. Okay, so we come from something which is information, also two parameters described in the Krauss operator, which are P, the probability of either the amplitude damping or the inverse amplitude damping happening, and gamma, which is the decay rate. And from those two parameters, we can establish some thermometrical parameters, which are those that characterize our interaction with the bath. So we can find out the temperature, which will depend on the probability P, and the interaction time, which will depend both on gamma, which is the decay rate, and as well on the temperature through the occupational number of the thermal bath, which depends on the temperature as well. Okay, so we have a model describing our interaction of our two-level probe with the bath, but we need to see how we can transpose that to the polarization domain. So let's divide the two problems. So we know we have an amplitude damping and an inverse amplitude damping. We start with the amplitude damping channel. You have your probe here. You send it through a polarization interferometer. So you divide the polarization components of your probe, and you, by putting a polarization rotation on the H component, you do exactly that. You move your population from the H component to the V. Okay, so this is the amplitude damping. If you want to perform the inverse amplitude damping, you just perform the rotation on the V components instead than on the H. And so you're moving population from the V to the excited state H. If you do both of them together with a probability P and 1 minus P, you have your generalized amplitude damping channel. We have performed this experiment, and Ephraim group has as well performed this experiment in 2017 at the same time. And our implementation were really similar. We both used a Sagnac interferometer as our simulation platform. The thing in which we differed was the way in which we implemented the decay rate, because in Ephraim's case, they used these half-wave plates, basically just matching the two interferometers I've just shown you. And the other way, which we instead did, was using a special light modulator. And we applied a mask on this modulator to have a phase phi, one time on one side to simulate the amplitude damping, so that it would only affect the arm of the interferometer where we had the H component, or on the other side to affect only the V component of our system, of our probe. So these are the results we obtained. You can see here you have H plus and V are the states in which the probe is prepared before the interaction. This is the excited state, this is the ground state, and this is a coherent mixture of the two. And these results are in function of the interaction time T between the probe and the bath. As you can see, in all cases, the two temperatures, so you have the hot and cold bath, are discriminated better for finite times. So before the probe reaches thermalization. And another thing that you can notice is that the time in which the state with coherence takes to thermalize is longer than the states of the where you have just the populations there. Next, going on, the other thing you can do is now perform a true temperature estimation process. So you have still your qubit probe and you make it interact with your thermal bath. And then instead of deciding if the bath was hot or cold, you measure the temperature, and you are interested mostly in determining the error associated to this measurement. The way we performed this experiment, the way you model it is still through a generalized amplitude damping channel. but we performed in a different way, basically changing again the way that the decay rate is introduced. I will go just briefly through the setup because we will need it later on. So just so you know what is happening. So we enter
Maybe
here.
I'll cut in one more time, Ilaria, if you allow me
Yes,
to.
sure.
Yes, there is another question in the chat
Sure.
from Paul Brummer
Okay.
asking what are the time units in the thermalization? What is the time axis?
This is a dimensional, non-dimensional time related to the. It's basically dictated. Let me just go here. It's basically dictated both by the temperature and the decay rate. So it's not a real.
Right. So I think just to be clear, you know, in both your experiment and in ours, what's really implemented is just one channel in a single step. And there is no real continuous time evolution. That's all being modeled, built into that matrix.
It's a simulated time, if that can answer maybe the question better. It's not a real time going by through the experiment. This I've already told you. Okay. So should I? Was that it, or there's? Okay.
I think so. Again, if anyone has an urgent, you know, clarification, just go ahead and speak up rather than hoping that I see it in the chat.
Absolutely. Okay, so as I was saying, I will briefly introduce this setup because we will need it later. So we are coming in from the right with our laser, going through our nonlinear crystal BBO to generate our single photons. So we will have our two single photons here, and one will be the ancilla, and one will be the probe. So this is the probe we are interested in finding out, in measuring then. And the way in which the ancilla will act as our thermal bath, and actually the interaction between the probe and ancilla will act as our thermal bath, because as we change the polarization of the ancilla, the interaction between the probe and the ancilla in our gate, which I will tell you about in a second how it's done, will increase. So we can, in the same way that we use a mask on the SLM or the rotation of the polarization, we can tune the interaction between the ancilla and the probe. The gate is a control phase gate, so a gate that applies a pi shift only on the vertical component entering to the gate, and this is realized with this partially polarizing beam splitter here, the central one. This is where the interaction happens, and this is a beam splitter, a polarizing beam splitter that has different transmittivity for the horizontal or vertical component of the polarization. So the horizontal just goes through, while the vertical component is divided, one over the square root of 3 goes through and the other is reflected. This means that if you have both your photons polarized with in the H polarization, they will not interact at all. They will just go like that. Okay. And then we also have these other two PBSs, because as you see, if we just add this one, the signal will be highly imbalanced between the H and the V polarization. So to even things out, we put these other two polarizing beam splitter rotated by 90 degrees on this axis, so that the transmittivity that was before the V polarization now is that the H polarization, while the V is unaffected because that would be 1, and so we balance out our signal between the two polarization. But there's no physical meaning in them aside from this implementation. And then we perform our polarization measurement on our photons. What we are interested into now, as I was saying before, is the error on our measurement. And we can approach it in two ways. We can go from a thermometrical consideration or from metrological one. From thermometry, we know that this would be linked to the fluctuation in the energy, because we will infer information on the temperature from the energy. So the two errors needs to be linked, and we can find this equation here that links our the variance in our temperature on the variance in our energy over the heat capacity squared. And this is always the number of resources. From a metrological point of view, we know that our error on the temperature will be lower bounded by the quantum Fisher information. So we can link these two results and obtain that the quantum Fisher information and the heat capacity are indeed linked by this relation. we can simulate, we can calculate, evaluate the Fisher information and this quantity for different initial state of our probe. So this is the excited state, this is the ground state, and these are combination between the two. And what you can see in purple, you have the quantum Fisher information, and in dashed red, you have this quantity here. And you can see that when your state is prepared in either one of the two populations, or either excited state or ground state, even out of equilibrium, the two things are equivalent. And let's start from the ground state. You see that, as we've seen before, the Fisher information is higher for lower times, so before reaching thermalization. So it means that here you can extract more information on your system. We will discuss in a second the crazy thing that is happening here, but for now, let's not go through it. And then instead, if you look at cases where you do have coherence, you see that the value of the Fisher information is greater, and this is exactly because you have coherence, which is absolutely not captured by the thermodynamical quantity, while it is captured by the quantum Fisher information. So we can do our experiment and measure the error on our temperature. As you can see, this is for the ground state. So when the probe starts in the ground state, and you can see that the results match the theoretical prediction. And then we go to what happens if our probe starts from the excited state. You see that, as I spoiled a few seconds ago, something weird is happening. And is that for some time, you lose all information on your system because the error goes to diverges. If you do the calculations, you find out that this is linked to the fact that it appears that in this first region here, your heat capacity is negative, but this is totally artificial, and it comes from the fact that if you are indeed starting in an excited state already, if you feed the energy to the probe, it can't go higher than that, so it will decay back to the ground state even if you are feeding it energy, and this is obviously a problem of the model. Is not something that is totally artificial. However, once a bit of time has passed, and the population is, the ground state has been populated back again because you're moving, you're feeding it energy, and this is going to the ground state, everything goes back to normal and you can perform your estimation.
So Ilaria, there you confused me yet again. That's a really interesting point. And I guess I do see, if we were talking about the relationship between energy and entropy, for instance, I'd see a sign flip where entropy goes to zero in both the lowest and the highest energy states, and therefore isn't monotonic. But I'm curious how exactly you're defining heat capacity. Are you defining a temperature even when you're in the excited state? So is it then a negative temperature?
Yeah, it's a negative temperature. Yes, that's the reason, basically.
Okay, so it's the negative temperature side that gives us.
Yeah, and I mean, as an experimentalist, the easier way I see it is that if you feed the energy to this two-level system, it can go up. You just have to go back down necessarily. There's nothing else. It can't stay there, and the only other thing you can do is go back to the ground state.
Except its energy actually goes down, right? It's just that the temperature becomes less negative, but the energy is still going down. Okay.
Yeah, absolutely. Okay. So these are the results regarding the simulations, and we have used, we have simulated using informational quantities, something which is predominantly a thermodynamical process. Now we ask, the system we have used is in itself a physical system. It's a logic gate, which we can use for other things other than simulation. We can use it for computing and all sorts of things. So we wonder if we can infer thermodynamical properties of this system and gain some information about it, like as for example, its efficiency. The answer is yes. This is the latest work we have done on this topic. And the idea is to use a two-point measurement scheme. So you have your two cubes. So in this scenario, before we have our probe and the ancilla represented our bath. But in real life, I mean, these are two qubits interacting. So even if we use them as a bath, this is actually, we used its interaction as a bath. Sorry, that was not correct. They're actually two qubits interacting. So we can consider a 2-qubit state at the beginning, starting at time 0. We evolve it so that we get 2 qubits at time t. And we divide the Hamiltonian of the evolution as the local Hamiltonian plus an interaction Hamiltonian. What we do is we perform a measurement on the energy eigenstate of the 2 qubits at the beginning and at the end of the interaction. And we only perform it on the eigenstate of the local energies. Okay, so we don't consider the even after we just perform on the eigenstate of the local energies. Okay, and by doing so, we can retrieve the probability, the energy probability distribution and the entropy production distribution. The way we do it is we use, this is still a control phase gate, even if it doesn't look like one, but is the exact same thing as before. I will convince you of that in a second. The interaction is happening here on this partially polarizing B splitter as before, which has transmittance equal to 1 for the H component and equal to 1 over square root of 3 for the V component. However, we embedded, and the gate is always a control phase gate, which flips the VV component into minus VD. The difference is that this time we embedded the gate into a Sagnac interferometer because we realized that the measurements we had to perform were extremely affected by the imperfection of our PPBS. And so we had to find, in particular, we found out that the transmission of our PPBS was not really close to being 1. And so when, let's say, you enter on with a signal H polarized on the PPBS, it should all go through. Some of it instead was being reflected. And this was messing up our measurement a lot. So by embedding it into a Sagnac, you see that if some H component would go on this red path coming from the signal, then it gets reflected. And when it arrives on this polarizing B splitter, instead of ending up here and being measured, oh, sorry, I didn't mean to do that. Instead of ending up here and being measured, it would just go through. So we will lose this component. Same thing, if you enter with a meter, which is H polarized, most of it would go through as it should. The part which is, so you arrive, you basically, the part which is here would go up here, would be reflected as well. So basically this worked for both meter and signal. And it's just a way to get rid of the imperfection of experimental imperfection that we had. But the gate works exactly as before. So as I said, you need to have your local Hamiltonian and your interaction Hamiltonian. So we found out how to implement these two Hamiltonian based on our system. And basically, in order to perform these Hamiltonians, this interaction Hamiltonian especially, what you have to do is you take your gate and you apply a rotation before and after your gate, so that for when the meter, which is your control qubit, is in the state 1, the other one gets rotated, basically. And so you can write the effect of the evolution of your states from an energetic point of view. So as I said, when the first qubit, so the meter qubit is 0, nothing is happening. When the first qubit is 1, then you have some evolution, which is this rotation over here. And you can map this rotation to the gate by considering that the rotation that you apply on this qubit is related to your energetic quantities, which are defined by this equation. But anyway, there is a mapping between the two that you can do. Okay, so once you do that, you can measure your probability distribution. And these are the ones which are non-zero, basically, are the one where this meter is set to 1, basically, and the other one is 0, 1. And so once you have those, once you have these, you can basically calculate everything, because you can calculate the moments of your energy distribution in function always of a certain simulated time. Okay, and you can calculate as well the moments of your entropy. The thing I didn't say is that since we are doing a 2-point scheme measurement, we don't have access to coherence because we are measuring before and after our system. So we destroy all coherence there is, but you still can evaluate how much this coherence should be. So as you can see, you don't have any experimental points here, they're just theoretical calculations. And you see that the profile of your coherence strongly resembles that of your entropy production. So you can infer that we couldn't check this experimentally, we are working on it actually, but you can think that part of your entropy production actually comes from the coherence that you have. The last thing I want to discuss, the last results of this paper was this, because once you have your, didn't mean to do that again. Once you have your entropy, your energy and entropy moments, you can relate them, obtaining a Landauer-like relation like this one, which you see here reported. So on the y-axis, you have the ratio between the energy and the entropy produced. And here you have always your interaction time. And you can see that the red one, the red dashed curve is just 1 over beta, which is the minimum you can do. The blue curve is the theoretical one. And you can see that here the data are way far from the theoretical prediction. And this is because here is where the interaction is stronger. So basically you are more sensible in this point to the imperfection of your system. And so it means that here we are either losing energy in some way which we are not taking account into the theoretical prediction, or we are producing more entropy basically. And the fun fact is that so we know how the efficiency of our system in a way which is totally platform independent, because we know that there is something going wrong with the system, but it's not specific to the error that we are seeing. So this is quite a general way to see how efficient your system is, basically. So concluding, the take-home message is, I hope I sent through, is that the informational and thermodynamical quantities are really connected. You can use informational quantities to infer information, consideration on your thermodynamical processes through simulations, but also you can use thermodynamical properties to estimate the energetic consumption of your logic gates. So the works we have performed are done by these people. So at the moment, the group is just Marco and I. It's just us two, but the work performed was also done by our previous PhD students and postdocs, so Valeria Cimini, Luca Mancino, Emanuele Roccia, and Marcos Broscia. The last work on the energetic of the logic gates was done in collaboration with Queen's University Belfast, Mauro Paternostro, and Università degli Studi di Firenze, Filippo Caruso, Stefano Gherardini, and Lorenzo Buffoni, while the two works on the thermometry part were done in collaboration with Vittorio Giovannetti, Antonella Pasquale, and Vasco Cavina from Scuola Normale Superiore. One tiny last slide before leaving you, just in view of the discussions which we will have later this afternoon, morning, I mean, depends, is that this is one of our activities of our group. But even if it's just the two of us, we are incredibly outnumbered by the number of projects we are following at the moment, as it's always the case. So our main research line is that of metrology, and in particular, we also apply that to biological and chemical sensors, especially chiral compounds. We are now moving ultra fastly towards ultra-fast quantum optics measurement, which is basically my main research line at the moment. And we also, do other things in the meantime, so fundaments, simulation, and some machine learning in collaboration with other groups. This is our context, and this is our group website if you want to check our activity out. And I thank you for your attention.
Well, thank you very much, Ilaria. We're all applauding, even if you don't necessarily hear or see all of it with this unfortunate setup. Fascinating presentation. There were already a bunch of questions in the chat, but maybe I'll just open it up now. If someone has a question, please go ahead and speak up. So some things never change. It's just like a meeting in person where I guess I'll have to ask the first question and people will maybe get awakened after that. I have to admit on your plot where the data fell so far below the theory and you argued that this imperfection was platform independent, I got very confused. I had really been thinking that you were showing that because of specific experimental imperfections, you were well below this bound. And I didn't understand where the claim comes from, that it, if I understood, that it's a more general observation.
Just let me go back to that if I manage. I'm trying. Yeah. Okay, there we go. Yeah, what I meant is in this case, of course, that depends on our, I was not clear enough on this, maybe. Of course, this is related to our own experimental error in our case, that is surely a misalignment, and so we lose some visibility in the setup. But what I mean is that this relation, this way of seeing things is only dependent on the method we've used of the 2-point measurement scheme. So if you were to implement the same protocol with another platform differently, this would surely give you a way to compare two experimental platforms which are way different, but with the same figure of merit, basically.
Okay. So that was just my theoretical misunderstanding, but I'm
I probably
by your response.
Sorry.
But among friends, I still feel compelled to ask the provocative experimental question, which is why such a huge discrepancy? That's a factor of 2 lower than it should be. Do you even expect that with the ideal setup, you should be able to saturate this bound here?
You also see it here in the entropy production and less so in the energy. And this is purely the fact of aligning the setup, basically. This is the main, and also we also have dark counts, but accidental counts. But the problem is that the entropy should go to 0 there, theoretically, you see. So a minimum discrepancies gets you a lot farther from what you should obtain. But yeah, I have to say that the imperfection on the partially polarizing beam splitters have given us a hard time. That's why we decided to go for this implementation in the Sagnac to try and minimize them. And we actually, before doing this, we had modeled, and it was not that far. I mean, the transmission was 0.9, non 0.90. I mean, so it was 10% off, but it's not that big. I mean, and still it was doing a huge effect. We also modeled it theoretically, and that was actually the cause of before reaching the final data I've shown you. It was even worse because of that. I think that maybe we mitigated it, but possibly we didn't get completely of that problem.
Okay, no, but since obviously we fight with very similar problems, it's interesting to see just how sensitive one can be, that even a 10% or smaller imperfection creates this factor of 2 in the final result.
Yeah, and this is something, as you seen from the data of the previous experiments, that was something that was not as relevant for those measurements. This is we use this gate also for other metrological purposes as well, in other works totally unrelated to thermodynamics, and it really depends on the measurement you're going to perform, how much that affects your outcome measurement. I mean, so yeah.
Are there other questions? Oh, it sounds like there's a tribble trying to ask them. Someone's trying to speak with an audio problem. I kind of thought I saw Paul Brummer trying to. Was that you, Paul? If someone was squeaking into the audio and wants to type into a chat, I can also read your question.
Okay, still working in the same way.
I know, it sounds pitiful. Someone's trapped inside their computer. We have to rub the lamp and let them back out.
I really hope that is not the case.
Someone else who's been silent so far have a question? Let me come back to oh, sorry, there we are.
Yeah, I had a good question. Great talk, thank you.
Thank you.
I was wondering about one of the expressions you had earlier on for tau in terms of the decay rate. I was wondering if your decay rate is normalized in some way to be less than 1 because of that logarithm term.
No, I think it all works as a normal time scale, but as you can see from the interaction, you basically tune your gamma experimentally. I think that is the closest, best answer I can give. So you are tuning your gamma so that in these graphs, which are here, you see your time goes.
Oh, I see. Okay.
Okay.
So I guess you're restricted to what you can.
Yeah. You choose your gamma accordingly so that works the way you want, basically.
Okay, thank you.
No problem.
All right, so you seem to have satisfied him, but gotten me more confused. So I still look at that log 1 minus gamma, and is there a reason that it's then physically meaningless to have gamma greater than 1? What gamma is dimensionless?
Oh, no, sure. Sorry, I'm in the experimental implementation. Gamma is a square of the sine of the angle.
Okay,
here.
so gamma is
so this is
not a decay rate. It's just a notational confusion. Okay.
Yeah, it's the parameter of you call it decay rate because in the Gauss operator that is the decay rate, but it's just this. It's actually sine squared of phi over 2. So yeah.
I guess
that is
maybe
right
it's equal to the decay rate in the small angle approximation. Right. Obviously, a decay rate could be as large as you like, but gamma for some reason is bounded.
Yeah.
So Paul was trapped inside his lamp, but managed to get a message out to me. And he asks whether you can say more about the relationship between entropy and coherence, because you alluded to it, but didn't really go into depth.
Yeah, this is going to take a while. All the animations coming nearly there. Okay. Yeah, so the point is that the idea behind it is that part of the generated entropy is due to the coherence you have during the interaction. Okay, but with the 2-point measurement, you cannot see that because you are obviously not measuring any coherence at all. We are actually Mauro Paternostro is working into find a new scheme in which we can actually access this information, well, the coherence information, so to see if there is actually a true match between the two. But that is the idea is to use an endpoint measurement, but at the same time you need to have information on your energy before and after the process, because otherwise you cannot calculate the momentum, and you cannot calculate the entropy, which ultimately depends on it. So it's a challenge. It's a theoretical challenge. So I don't really know what are. I mean, aside from the fact that in this way you cannot do it because you're not measuring coherence. I don't know what the problem is when you do what the endpoint measurement and try to, from a theoretical point of view, I don't really know where the complication stands, but surely experimentally I can see that it's not super feasible to do, but yeah.
So let me try to pick up on that. I mean, as you pointed out, we worked on this a little bit a while ago. It's been a few years since I've done anything related to it. And interestingly, you and I never really took the opportunity to discuss this before.
Yeah.
But, you know, I was intrigued by that original paper from Terry Rudolph's group proposing that coherence would have this power. And when we did our experiment, I had a hand-waving view of why all of this is. And I'm curious to run it by you and see if you just agree or disagree entirely, which was that normally when we build a thermometer, we wait for it to thermalize, and then we just use that final population as the measure. But at least depending on your thermalization model, and in the case that we're both discussing here, there are two things that change. There's the equilibrium, depends on the temperature of the bath, but the thermalization rate also depends on it. So by sitting at times before you've thermalized, you're not just probing that final equilibrium condition, you're probing something about how quickly it's approaching it. And there are regimes in which that can be more effective. Once you know that, my argument was that there's a factor of 2 difference, at least, in the case of simple, homogeneous processes, between the population decay rate and the coherence decay rate. And that their regimes were making use of that difference means that at least at certain times, the coherence will be more sensitive than the population. Now, why that ever meant that the optimum would rely on the coherence, I didn't see. I understood that there'd be specific moments in time at which the coherence would be more sensitive, but I think that the actual results you're showing are that even after you optimize over time, it's still better to use states with coherence. And are we basically looking at this the same way? Do you think I'm right about that?
I think you are, but also from the implementation of the thermometer, that was not entirely clear. But also there you have the problem that if you want to measure, for example, the measurement we did was measuring an operator, which turned out to be the energy for the ground and excited state, but is a weird combination for the coherence. So it was not that evident that would provide. Of course, as you said, the time frame, yes, that is for sure. It was not that evident that would provide a better. I agree. So yeah.
Are there further questions? Oh, there's yet another one from Paul Brummer. Can you do 2 baths, which would bring you into the interesting non-equilibrium steady state regime?
In which case? So
I imagine what he's thinking of is having your probe coupled to 2 baths at different temperatures, but with different coupling rates. And I'm not sure exactly what he'd want you to measure, but it would be a more interesting regime to study experimentally, I suppose.
Yeah. Could you do it experimentally? Yeah, I mean, so I think not the easiest thing, but I think it could be doable, maybe. I don't know. I would need to think about it, but surely something that sounds interesting to look into. So.
I was wondering, your title, both of your paper and of the talk, are really provocative when we think about the energetic cost of quantum gates or simulations. And of course, you came into this from the metrology side and then did the flip. But I wanted to know if you had any bigger take-home message about anything we might learn about limitations on the energy requirements of quantum computers, for instance, or quantum simulations.
I think the only thing that you can infer is this one in the end, and these can give you a meter to say if you're how much efficient you are being in the end, and as I said before, I think the cool part of this is that this doesn't depend on this is very general in terms of how you develop it. So that's it. But yeah, of course, thinking along this line. I mean, here, for example, that is very weird in my opinion. But here in Italy, that when we published the paper, there was this huge media reaction to it as a, how much a quantum computer is gonna consume. But it's a bit stretched in my view, in the sense that in the end you are just assessing how efficient is your gate.
And of course, very often when we do these simulations, we don't even have an energy difference between the states. But I guess in my mind, the big picture is, what was Landauer studying? He was interested in what the fundamental minimum energy cost or heat dissipation for a computer was, and recognized that it had to do with this erasure step, but also that you could dispense with erasure and do reversible computing that wouldn't have to dissipate at all. And that's kind of the starting point in my mind for a lot of quantum computing, right? That it is reversible and unitary. So I'm just curious whether you still agree with the conventional wisdom, which is that quantum computing needn't have any energy cost at all because it is truly reversible, or whether you're saying there are regimes we need to move beyond that.
I mean, the example we have considered here is in principle a unitary transformation, aside from the fact that then we we have the problem at the end where our data don't match, but theoretically it is a unitary transformation. The reason why you still see an entropy is because here you're measuring on an Hamiltonian, which doesn't include this bit. You're just measuring on the local part, so you're not unitary in that sense. So yeah, I mean, in principle you can, but then if you need to measure stuff, possibly you are back to the same problem, I would say.
Okay, thank you very much. All right, there's time for another question if anyone has a last question or comment to make. But otherwise, please join me in thanking Ilaria one more time for an interesting work and a great talk. And I will say goodbye to most of you, and we're going to just stay on this Zoom line for a set of individual meetings, I think beginning with Paul Brummer, hopefully.